Nobody wants to come. It's a sad thing. One participant. Hi, Jasmina. Hi, Jasmina.
Hello, how are you?
Doing fine. You a bit tired? Did you just finish the test?
No, I did it this morning around 12.
How was it?
It wasn't that bad, it was pretty easy, but I noticed that there was a duplicate question with the writing, like the ones that you have to show your work on.
I will check that. I will.
Yeah, I don't remember, I think it was 33 and 35. I think they were the same.
Um, if if it's if it's if it's not if it's extra points, then I'll just discard the one. But I didn't think I saw that. Hmm. Let me look at it. Well, people are joining here.
All
Uh,
right.
did you get the last question? That was the bear question.
Uh, oh, yeah, that took me a while to do, but I think I figured it out.
Was it C5H5N?
Did I get that as the answer?
Yeah.
Nope.
We'll give you some points, I'm sure. Don't worry about it.
well.
Let me see. Oh yeah, I need to do that. I got 3 of you, and who else is here? I know Jasmine is here. Who else is in here?
Vanessa is.
Hi, Vanessa.
Hello, how are you today?
I'm doing fine. Did you take the test for me today or not?
The test.
You don't have me for lecture then, do you?
No, I do not.
Okay. Because some of the other people had me for lecture. I am checking on that. I am checking on that, Jasmina.
I was very concerned there for a second.
I'm not. Was it the aluminum foil one? Yep. I changed this at the last second. Okay. So I'll just give you 11 points for that. Okay, Jasmina?
Okay. Yeah, I noticed that there's a duplicate, and I was like, oh.
It is a
Okay.
duplicate question. What happened was I changed the test around at the last minute, and I got a duplicate question in there. Wow, there's only. Have I been setting these up for 7:30?
Nope.
No.
It's usually been 7:15, right?
Yeah.
Yeah.
Okay, we may have a private audience here. So maybe others are thinking it's 7:30. I don't know. And Vanessa, you definitely only have the lab, so you had to have accessed this through the lab. I sent it out to the right people.
Yeah, I got it through your email.
Okay, good enough. Do you want to just get started and we'll let them pick it up as they pick it up?
Sounds good.
Yeah.
Okay. It'll get you out of here quicker. Okay, why is that not? There we go. All right, you see the empirical formulas? Do you see the empirical formula PowerPoint?
Yes.
Yeah.
Okay, did you both read the lab or are you just kind of scuffing off on it?
I have my lab up at the moment.
Okay, but have you read through it?
Yeah.
Jasmina?
I read it briefly for the pre-lab.
No, that's fine. That's fine. Basically, what is happening? You need to get the masses of all the things that are involved here. You have a formula that you don't know. That formula is CuX Cly dot ZH2O. Okay? You don't know what the subscripts for the X, the Y, or the Z are, and you have to determine that. All right? Fair enough?
Yeah.
So basically, what you have to do is you have to get the gram totals of each one of these things. The water, the copper, and the chlorine. Okay? So basically, you weigh the crucible, and then you put the hydrate in. Now, the very nice thing about copper chloride is when it's a hydrate, it's a nice green crystalline, blue-green crystalline substance, okay? So what you're gonna do to that blue-green crystalline substance is you're gonna heat it while it's in the crucible. So you've weighed it with the hydrate and the crucible, you've let it cool, then you have weighed it, you've heated it again and cooled it and reweighed it. If the weights are close, within about 0.05 grams, you're done. You don't have to reheat it again. And the reason you want to get the weights close is because you want to make sure that you have driven off all of the water. Now, the great thing about this experiment is when it is the hydrate, when it is around water, copper chloride is blue-green. When it is anhydrous, it's brown. So you can literally see when it's anhydrous. Okay? Then what you're going to do is you've reweighed the crucible and the anhydrous. Then what you're going to do is you're going to do a very, very silly thing. You just heated it to drive off all the water. Now what you're going to do is you're going to add water to it. When a chemist says quantitatively transfer, what that means is you want to get every little bit that's in one container into another container. So basically you kind of knock all the brown crystals into a beaker. Those that you can't get out, you take a squirt bottle, rinse it down, pour that into the beaker. Then you raise the amount of volume up to about 15 to 20 milliliters. Next thing we're going to do is we're going to take a piece of aluminum wire, and we're going to take it, we're going to put it, the coil's not going to be very, very tight. It's going to be a fairly loose coil, but we're going to make it into a coil so it can submerge into the copper chloride solution. Again, we're fortunate from this reaction because when you put the blue crystals from the hydrate into water, the solution comes blue. Where do you think the blue color is coming from?
Chloride.
Okay, that's one option. Vanessa, have you ever seen hydrochloric acid?
Yes.
What color is hydrochloric acid?
Isn't it clear?
It's clear. So do you
But not
expect
chloride.
so do you expect the color to be coming from the chloride ion?
No.
What do you expect it now to be coming from?
The copper.
The copper ion. Okay? So the copper is giving you the solution. So if we take the copper out of the solution, the blue color, what's going to happen to the blue color?
It's not going to be blue.
It's not going to be blue anymore. The copper is going to be pulled out of the solution. That's going to leave back a clear solution. So again, we have another color indicator to realize when our reaction is done. So what we're going to do, and basically this is a reaction we're doing a single replacement reaction. Aluminum's kicking out the copper to make aluminum chloride, and we're making copper metal. So it's going to take an hour for this to happen. Believe me, it's just trouble. People were banging off the walls waiting for this solution to get done. Now, an hour later, the color in the solution is going to be gone, but what color is going to be on the wire?
Blue?
No. What color is copper, Vanessa? Copper metal.
Oh, like a brownish yellow?
Brown. So you're going to have this rust colored solid that's going to coat all over the aluminum. You're going to add a little bit of HCl to make sure that all the aluminum chloride stays dissolved. Then you're going to weigh a filter paper. You're going to knock all the brown solid from the wire into the solution with a glass stir rod. Why don't you use an iron stir rod? Any idea?
Because it's metal on metal.
Specifically, what metal?
Copper on iron. The copper will get on.
But we have, at that point, that's copper with iron. Is anything going to happen with the copper and the iron?
Wouldn't they react?
I'm sorry?
Would they react?
Iron is more active than copper. Nothing's going to happen, and both of them are metals anyway. But what is possible is that the iron or whatever metal is made up by your spatula could react with the aluminum chloride. Okay?
Oh, okay.
So you don't want that to happen. As a matter of fact, that's one of the reasons why the balance pans are so stained in the chema area, is because there's been a lot of copper chloride that has been spilt on them. So in any case, that's just another sideline. So we have knocked all the copper off and we've got it into solution. We're going to use a special device called suction filtration. We're going to put the filter paper in this device and we're going to knock all the copper around. We're going to pour that solution in. We're going to make sure we get all the copper onto the filter paper. So we've effectively transferred all the copper onto the filter paper. So we're going to dry that filter paper and then weigh it. Whole experiment's done. Any questions about what we're doing with the experiment?
No.
Pretty straightforward?
Yeah.
Okay, so now let's get into what's really happening. All right. First part of this is just the same thing as the part we did last week. Remember, last week we were finding the mass percent of the water in the solutions. So we had the hydrate that we weighed, and we heated that hydrate, and we got the weight of the anhydrous. To get the weight of the water, all we got to do is subtract the hydrate and the anhydrous. That'll give us the weight of the water. So we have the weight of the crucible. We have the weight of the crucible and the hydrate. We subtract the two, we get the weight of the hydrate. We have the crucible and the powder after heating. We have the weight of the crucible. Now we have the mass of the anhydrous. So to get the mass of the water, all we got to do is take the mass of the hydrate and subtract the mass of the anhydrous. That will give us the mass of the water. We good? We good?
Yep.
Okay. I don't know where I'm going with this. Okay. So what I did was I made up a solution. Instead of making copper chloride, I messed with iron bromide, and I don't know what the solution of iron bromide is. All right. So I have the mass of my filter paper. Okay. I have the mass of my filter paper and iron. I subtract out the mass of my filter paper. I now have the mass of my iron. Now I got to ask you a question. Do you see this mass of anhydrous there?
Mm-hmm.
Okay. What actually is the anhydrous made of? What's in it?
The aluminum chloride mixture.
What did we start with here? In your reaction, we started with?
Oh, the copper chloride.
All right. Is there any more water in the anhydrous?
No.
So if I have the anhydrous sample and I know how much the copper weighs, can you tell me how much the copper chloride weighs? I'm sorry, back off. I know what the weight of my anhydrous is, and I also know what the weight of my copper is, right?
Mm-hmm.
Can you tell me what the weight of my chlorine is?
Yeah.
How?
By subtracting the weight of the copper and the weight of the anhydrous.
There we go. Okay. All right, so I have the weight of my anhydrous salt, okay? I subtract the weight of my iron from it. Remember, I got my iron by subtracting the filter paper and iron, and the filter paper, I got the mass of my iron. I just subtract my mass of iron from my mass of anhydrous salt. This gives me the weight of my bromine. Now, remember when I told you, or Vanessa, what I told my lecture class is the first step in doing any empirical formula problem is finding the weights of everything. That is
Okay.
also the hardest step.
Yeah.
All right. Next step is we're going to find moles of everything. We now have the weight of bromine, we have the weight of iron, and we have the weight of water. So we're going to turn all the masses to moles. Then we're going to divide by the smallest number of moles. And if necessary, we're going to use a multiplier. My iron weight 0.321, divide by the atomic weight, I get 0.00575 moles of iron. I take the 1.376 grams of bromine, I divide that by the molecular weight of bromine, I get 0.1722 moles of bromine. Divide by the smallest one, and I get approximately 1:3 ratio. So the empirical formula of my salt, of this particular salt, is iron bromine 3. Everything makes sense so far?
You got that 3, the subscript of bromine from the
Molar ratio. From the
Okay.
molar ratio, okay? The first thing we did was we turned the weight of iron into moles of iron. We turned the weight of bromine into moles of bromine. Then we looked at these two numbers, and we looked at them and we determined that the iron was a smaller number. So we divided the moles of iron into itself and got 1. We divided the moles of iron into the moles of bromine and got 2.99, which is effectively 3. That way we know that the molar ratio between iron and bromine is 1:3. And since the subscripts are the molar ratio of the two elements, we know the subscript for iron is 1, the subscript for bromine is 3.
Okay. I do have one more question. Where did you get the grams for iron? That's not off the periodic table.
This,
Is that given?
the 55.85.
The 0.321.
Okay, remember when we did our reaction, we put the aluminum wire into the solution. Remember that, Vanessa?
Oh, okay. Yeah.
Then we weighed the filter paper. We scraped off all of the iron, and we poured the solution through the suction filtration device. All the iron got left on the filter paper. We dried the filter paper out, and we subtracted the iron and filter paper from the weight of the filter paper. That gave us the mass of the iron.
Okay, thank you.
Jasmine, are you good?
Yep.
Okay. Now, when we did this, after subtracting the hydrate and the anhydrous, we came up with the grams of water. We multiplied that by 1 mole over 18.02 grams. This gave us 0.0345 moles of water. I'm going to take that and divide it by the moles of iron that we just got. I take 0.0345 and divide that by 0.00574. I come up with a number of 5.99. So therefore, there's a ratio of 1:6 iron to water. The overall formula is then going to be FeBr3 6 H2Os.
Okay.
Are we good, guys?
Yeah.
Now, there is an assumption. There is an assumption that we just make, that when we're doing this particular problem with this particular experiment, as it is written, we have made an assumption. Okay? This is where you can use that last box in the results section.
Okay.
If you figure out what the assumption is, you'll get 5% extra credit for the results section, okay?
Yeah.
Sounds good.
Okay, now, something that's important. When you're considering the elements of the salt, if you divide the smallest moles of the element by the largest and you get a fraction, you have to keep multiplying that fraction by integers until you get a reasonable number. Is that something you both know?
Not particularly, no.
Vanessa, have you gone through empirical formula problems?
Yeah, it's been a little bit, but
How long ago did you do them in lecture?
I don't remember.
Okay.
Sorry.
Who do you have, Dr. Musgrave?
Yeah.
Okay. This is a rule, okay? When you did that dividing by the smallest thing, sometimes when you do that, you come up with the fraction, like maybe 1 to 1.333. Okay, Vanessa?
Okay.
You can't have a fraction of an atom defining a compound. Have you ever seen a fraction of an ion defining a compound?
No.
Therefore, you got to make a whole number ratio out of it. Okay? So if you have 1 to 1.3, multiply both by 2, and you get 2.6, 2.67 to 2. Is that
Okay.
are those whole numbers?
Yeah.
2.6 is a whole number?
No.
Okay. So multiplying by 2 didn't work. So you go up, you try 3. I multiply 3 times 1.33 and I get 4. I multiply 3 by the 1 and I get 3. So my ratio, instead of being 1.33 to 1, is now 4 to 3. It's the same ratio, but now I have whole atoms. Does that make sense to you? Does that make sense to you, Vanessa?
Yes.
Okay. Now, when you're comparing one element to the other, you want to do that. You want to multiply the fraction by integers until you get whole numbers for both atoms. When you're comparing the water to the salt, the coefficient in front of the salt is always 1. Always. So when you're doing it for the water, just round up. Do not multiply by an integer. Because if you multiply the water's coefficient by an integer, you have to do the same thing for the salt. But the salt always has to be 1. So with the salt, I want you to just round it up. If you're comparing one element to another within the compound, that's when you use an integer. Are we good, guys?
Yes.
Okay. Now I'm just going to give you a slight example of that. And then we're going to get out of here. You have a compound of aluminum and sulfur with water in. You started off with 2.625 grams of the aluminum sulfate. You heated that and reweighed it. It weighed 1.391. You then placed it in water, aluminum added, and you precipitated out 0.500. Let's do this. And you precipitated out 0.500 grams of aluminum. Okay? So we know we have 0.500 grams of aluminum, right?
Mm-hmm.
The weight of the water is the hydrate minus the anhydrous, or I have 1.234 grams of water. Okay? I got back 0.500 grams of aluminum, so I take the anhydrous, subtract the aluminum from it. That gives me the weight of my sulfur. I've got all 3 weights. Now I divide by the atomic weights when I have aluminum and sulfur, and the molecular weight when I have water. I do that out. I get 0.0185 moles of aluminum, 0.0684 moles of water, and 0.0278 moles of sulfur. I divide the moles of sulfur by the moles of aluminum. I get 1.5. Moles of aluminum by moles of aluminum, I get 1. I've got a fraction, so I have to multiply this by 2 and this by 2. So I get 3 for the sulfur and 2 for the coefficient for the aluminum. Are you with me so far?
Yes.
All right. Now, when I'm going to compare the moles of water to aluminum, I take the moles of water, divide that by the moles of aluminum. Lo and behold, I get another fraction. Because I can't do this. I can't make the coefficient in front of the aluminum sulfate more than 1. That has to be a 1. So when I get a number like this, I have to round it. So the formula of my salt in terms of aluminum and sulfur is Al2S3 dot 4 H2Os. Does that make sense to you?
Yes.
Okay, that's really all I have for you tonight.
Well, thank you.
Have any questions? It's been a rather intimate group.
I'm good.
Jasmine, are you good?
I'm good. Thank
Okay.
you.
The test, Jasmine, will be graded by probably noon tomorrow. I'm hoping.
All
Okay.
right. Sounds good.
All right. Take care, guys. Vanessa, I'll see you next week. Jasmine, I will see you on Thursday for stoichiometry.
Yep.
Vanessa, where are you right now? Just as I've got you. Where is Dr. Musgrave? What subject are you doing?
We just took our test, so I'm not exactly
How far did you
sure.
go in your test? Did you go to stoichiometry?
No. So he's probably exactly where you are.
Didn't do gas laws?
No.
I'm just trying to find out, Vanessa, because I'd like to know. I'd like to gauge where I am in terms of him, because he generally speeds through this stuff, especially the first couple chapters of Chem 1. Okay.
I'm not exactly sure where I am for my personal. It's hard for me to follow him.
Did you go through this kind of stuff? These kind of
Yeah.
problems? You've been through these kind of problems.
Mhm.
I don't know where you are either.
Yeah, I'm not sure. Our whole class is like self-paced.
Okay.
So it's more of you have all of these assignments to do within the next 4 weeks, and then there's the test.
Okay.
So at your own pace, and then all those Zoom meetings are recorded. So I think
So he doesn't have a live Zoom meeting with you?
he does, but I think he changed the times for it, so I'm unable to meet at that time.
Okay. Again, all I'm doing is I'm just trying to gauge where I am in relation to him. That's all.
Yeah, I mean you're good for me.
Okay. Good enough.
Chemistry is just not easy for me.
A former student of mine succinctly put it. Chemistry is very, 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 very hard.
Yeah, it's challenging.
And I may have left out a very. Okay, guys, I'll see Jasmina. I'll see you on Thursday in the morning, Jasmina.
Yeah, I switched to the morning one.
Okay, I'll see you in the morning. Vanessa, I'll see you next Tuesday.
Thank you. I'll see
Take
you then.
care.
Take care.
Bye.
Bye.
Bye-bye.